Dr. Rico here. This is a lecture from my course on robotics. The syllabus link is in the description. All right, welcome to Kinematic Models, part of the chapter on robot mechanics. We are interested in the kinematics of bodies. There are two branches of mathematics of particular importance for these descriptions: geometry and algebra, sometimes considered the two branches of mathematics. Geometric objects of interest to us include the following: points, free vectors that have length and direction, bound vectors that have length, direction, and a point of application, and reference frames, origin, three orthonormal basis vectors at the origin obeying the right-hand rule. Okay, that's what a reference frame is comprised of. In contrast to these geometric objects, the algebraic point of view has its basic objects: arrays, ordered lists of numbers, and matrices, ordered lists of arrays. These algebraic objects will represent geometric objects. For instance, we're all familiar with a geometric vector V representation as an algebraic array. V, the vector, is represented by this list of three components. This algebraic representation has an important caveat. It is written in coordinates with respect to a specific reference frame x, y, z. See the x, y, and z components listed there. It is this quality of algebraic representations that separate them so fundamentally from geometric representations, which are independent of specific reference frames. As one would expect, each representation has its associated concepts and relations. For instance, geometry has angles, curves, and manifolds, whereas algebra has transposes, linear maps, and eigenvalues. Many of our analytic tools are algebraic. However, it is usually easier conceptually to work with geometry. With these mathematical tools, we can describe the following of particular importance to kinematics: positions and orientations of bodies, frames of reference and changes of coordinate, and motions of rigid bodies. A rigid body in space. The state of a rigid body in space is completely described by a vector representing position and a vector representing an orientation. We call this description a body's pose. We call the minimum number of coordinate variables required to describe the pose of a body its degrees of freedom. Generally, we require 3 position coordinates and 3 orientation coordinates, such that a body has 6 degrees of freedom. However, constraints frequently reduce this number. For instance, we are accustomed to treating certain bodies as being constrained to the plane, meaning it has 2 positional degrees of freedom and 1 orientational degree of freedom. So 3 degrees of freedom in toto. Multiple rigid bodies. Describing the state of a system of multiple rigid bodies is a matter of accounting for the pose of each. Therefore, in the general case of n bodies without constraint, the system has 6 times n degrees of freedom. A robot's workspace is the Euclidean space, sometimes taken to be R, the real numbers, or R2, but really R3, right? The real space, accessible to the robot considering its geometry, constraints, obstacles, etc. The aggregation of rigid body poses in a system is called the system's configuration. Okay, I'm going to use this a lot. More precisely, a robot's configuration Q is the minimal set of coordinate values in number equal to the degrees of freedom that describe the poses of all its rigid bodies. Similarly, a configuration space is the set big Q of all possible configurations subject to constraints. The configuration space is not the workspace, common misconception, which corresponds to the volume of actual mechanical space. The configuration space is an abstract space of possible coordinate values. Joints. Joints among rigid bodies are connections that constrain their relative motion. The most common types of joints constrain relative motion to a single degree of freedom. If a joint constrains to only translational relative orientation, it is called prismatic. If it constrains to only orientational relative motion, it is called revolute. Single degree of freedom joints are always one or the other, either prismatic or revolute. Conventional schemes of each are shown in this figure. Okay. On the left, we have prismatic joints, the schematics thereof. And on the right, we have three different revolute joints, schematics thereof. We see in A1 that this prismatic joint allows these two links, we'll call them in a moment, but these two bodies to move relative to each other in one translational direction, in line with each other, right? In A2, we see that there are two perpendicular bodies that are constrained to move along this single translational degree of freedom. And in A3, we have a very similar schematic of the same type of joint. In B1, we have two collinear bodies that can spin relative to each other, that can rotate relative to each other. In B2, we have two bodies who have a point of intersection, and that point of intersection allows them to rotate along this joint relative to each other in this way. And in 3, we have a joint that is, it's not clear what the other body would be, but we have a body coming off here that can clearly be constrained to rotate about this axis that's shown. When rigid bodies are connected via joints, we often refer to them as links. Links are often shown schematically as lines, as we've done above. The orange lines in this figure are representing the links. It is also possible to have a joint between a body and a reference or ground in space. Typically, this reference or ground is taken to be fixed. Recalling that the degrees of freedom of a body are the minimum number of coordinate variables required to describe its motion, and realizing that a joint reduces the relative motion of two links, we can see that joints tend to reduce the degrees of freedom of a system of rigid bodies. In most common cases of a manipulator robot with a single sequence of n links connected with 1 degree of freedom joints, with one end joined to ground and the other free, each link adds only a single degree of freedom out of its potential 6. So the entire sequence of n links has only n degrees of freedom. Kinematic chains. What we have just called a sequence of connected links is called a kinematic chain. The example of a chain of n links connected by 1 degree of freedom joints, joined to ground at one end and free at the other, is called an open chain. Robots with such configurations are sometimes called serial robots. The free end can have various tools attached. For example, a paint sprayer, cutting tool, gripper, etc. and is called the end effector. Consider if the end effector is moved to some intermediate link in a chain and both ends connected to ground, usually displaced from each other. This is called a closed chain. A robot with a closed chain is sometimes called parallel, although the type we introduce next would more frequently receive this label. Consider the fact that at times a joint connects more than two links. Kinematic chains with these joints can have multiple branches or chains themselves. Frequently, one or more of these branches will not have a free end. Rather, they connect to another branch or, most often, connect to some ground location. A robot with only closed chains and one or more end effector on intermediate links is called parallel. These types of considerations of robot links and joints are called topology. For instance, serial and parallel are two different topologies. As is summarized in the following table, the performance and therefore applications of the serial and parallel topologies are quite different. New performance considerations in the table are defined as follows. We haven't considered yet payload, which refers to the ability of a robot to move massive loads. Speed refers to how quickly a robot can change its configuration. Dexterity refers to how changeable is its configuration. Here's the table. We compare serial and parallel topologies in the table along four different performance categories: payload, speed, dexterity, and workspace. So we see that a serial topology robot has relatively low payload, so it can't bear as much weight. It is relatively slow. It has high dexterity, and it has a relatively large workspace, whereas a parallel robot would have a high payload. Tends to come with the fact that you have typically multiple connections to ground. Adds a lot of structural rigidity. Okay? Speed becomes much faster in many cases. Dexterity, low dexterity. Okay? It's more bound. It's not as dexterous as the serial robot. And it has a smaller workspace. It isn't able to move through as much of the space. Sometimes considered part of a kinematic chain itself, and other times considered part of the end of an open chain, a wrist may be part of the topology of a robot, especially when dexterity is important. A wrist is usually composed of 1 to 3 short links joined by revolute joints. The primary purpose of a wrist is to change the configuration of the end of the kinematic chain, which is particularly important in manipulation tasks. Direct kinematics. The calculation of an end effector's pose as a function of the configuration coordinates is called direct kinematics. Consider what this means for a typical open chain robot manipulator. In some configuration, the links each have a pose, but the pose is not explicitly given in the configuration. Rather, the poses can be calculated by starting at the grounded end of the chain, a known position, and given each joint's coordinates, the pose of each successive link can be derived. This problem turns out to be reasonably straightforward with linear algebra via the concatenation of linear maps called rotation matrices. See Below and Smith for a nice introduction, Siciliano et al. For thorough derivations, and Below and Lewis for a mathematically rigorous treatment. Inverse kinematics. The problem is that if we would like the end effector to be in some specific pose, how can we determine a corresponding configuration? This is the problem of inverse kinematics. As you can imagine, it's a very important problem because what we can directly control in a robot are its actuators, usually motors at joints. That is, we can only directly control the robot's configuration, not the pose of its end effector, which must be indirectly controlled through the configuration. This inverse problem is usually nonlinear, large, meaning many variables, and may have multiple 1 or even 0 solutions. Fortunately, there are excellent numerical solvers for this problem. However, these are far from a magic bullet and must be approached with caution. See Bullo and Smith for a nice introduction, Siciliano et al. For thorough derivations of some specific but useful problems, and Bullo and Lewis for a mathematically rigorous treatment. Okay, that's all I have for you. See you next time.